Okay, I want to make a video to help explain what we were kind of seeing in the lab last night. And this was a great situation to have happened. It was kind of unintentional, but at the same time, it's a very good lesson in PLC programming. And that is the idea of having duplicate coils in the same program, meaning that on two separate rungs, we're basically controlling the same coil. So here we have conveyor B coil to turn on, and then also in rung 2 we have conveyor B. And this was the way that a lot of you did this, and to be quite honest, this was actually a very good attempt. This was based on what you've done in the previous labs and kind of just leaving it to you to kind of figure out. You went this way, and quite honestly, this was good thinking in trying to program this. But what was unknown to you is that there's a little bit of a there's a little bit of an issue here. And it's interesting because the PLC, the Micro820, actually let us do this. It let us put the coil twice in the same program, and it let us download it to the controller, and it did not create an error. It wasn't considered an illegal operation. It didn't even warn us of the fact that there was duplicate coils there. There's another term for this you'll find perhaps in some documentation, and that is it's called a destructive bit, which is an interesting term, but duplicate destructive bits. Some programming software would actually have warned us of this condition, and in some software it might have actually prevented us from doing it without overriding a setting. But the Micro820 just let us do it with no issues. So let's talk about a little bit about why this is a problem, which some of you have saw this last night. So first, it kind of goes back to some basics, and that is the idea of the sweep, right? We talked about this a few weeks ago, and that is how does the PLC actually operate? So it operates on a sweep. So at the top of the sweep, the first thing we do is we scan the inputs coming from the field, or the inputs in the input table. Then we go into solving the logic. And in the last part of the sweep, we write to the outputs. And then we repeat this cycle over and over and over again. In the order of, a cycle is, in the order of, just a few milliseconds, depending on the size of the program. So this sweep is happening, multiple times a second, so fast that we can't even really discern what's happening. Can't really see it necessarily in the logic playing out. It's happening so fast. So what that means back on our program is that once we come to that solving of the logic, what really happens in the controller is we start with rung 1 and we go top to bottom, left to right. So when this program starts and it's running, it goes to rung 1. It scans across from left to right to try to solve the logic or find a true path to get from here to the other side of the rung, essentially. And if there's no true path, then basically these two outputs would be not on, told to still be 0. Then it goes to the next rung, rung 2, and it scans across left to right. Does the same thing. We've got a branch here, right? So it tries to go this path. It finds no way, there's no path all the way to the coil. It comes to the branch and finds no path. So these two coils are therefore turned off as well, right? That's fairly straightforward. But let's look at the situation that we were facing last night. So the concept was that we had, two main functions to our program. One was when we turn on the start switch, we were going to move the box down the conveyor A. We were going to turn on conveyor A and conveyor B at the same time until it got down to the photo eye and told it to stop. Then, second part of the program was when you turned on the load switch, it was going to have to turn on conveyor B and the load conveyor. So conveyor B was going to be controlled by two different kind of pieces of logic, shall we say. And the reason for that was because we had to activate the B conveyor to kind of push the box off the conveyor. If we didn't turn on the B conveyor, the box would not move onto the load conveyor. So it's a little bit of an unintended consequence again when I kind of drew this up, but what happened here is a great lesson. So most of you did what I have on the screen here, where rung 1 was the start switch going through the at entry, basically the start switch, and then the conditional of if the photo eye at the transfer entry was activated or not, and then that would turn on both conveyor A and conveyor B. And when we kind of latch in on itself, we could pick either A or B, or some people put A and B in series with each other. A little bit redundant. Not necessarily have to do that. You could kind of just pick one, but I picked conveyor A here to kind of latch it in. Since conveyor B was in parallel, anytime A is on, well, therefore B would have to be on, right? So when we put the start switch on, and if the photo eye condition was, true, then we can basically pass through and turn on conveyors A and B until the box reached the photo eye. All right. Then rung 2 was when we turned on the load switch, the second switch. We would basically go into, we would start the load conveyor, and we would start conveyor B also, and we would move the box onto the load conveyor until it reached the sensor that detected the box was fully onto the load conveyor, or the transfer conveyor, I should say. And we would latch this in with the load conveyor motor. Again, could have had load conveyor and conveyor B or conveyor B here, but I chose the load conveyor for this example to latch it in, right? Because basically these two would turn on. So the problem we were experiencing last night was that at certain times conveyor B would actually not be energized, even though you would think that it would have been. And here's kind of why. So I'm going to use, so built into the CCW software is a Micro820 simulator. So we actually can test and do some things without actually having to have a real controller in this software. So the Micro820 simulator, these are the inputs on the top and these are the outputs on the bottom. But I went ahead and used the exact same tags that you would have had in your lab last night. So embedded IO, embedded input 0, 0 for the start switch, embedded input for 1 for the load switch, and then the bool in 0 and bool out 0, 1 to match what the factory IO scene would have used. So let's go with condition 1. Condition 1 is I'm going to start the conveyor A and conveyor B motor to move the box down. So I'm going to turn on the switch by just clicking my simulator input. That turned on the start switch, and we see that we have conveyor A on, but conveyor B is not energized. So the reason for that is going back to how we solve the logic, right? So we start with rung 1, we go left to right. Then when we come to rung 2, we go left to right. Well, rung 2 basically is saying, there's the logic on rung 2, the load switch is not on and we don't have the latch. So therefore, rung 2 is telling conveyor B that your condition is false, you should be off. Rung 1 is saying you should be on, but rung 2 is saying you should be off. And being that rung 2 is the last rung in the program, that's kind of the one that wins out. In that it's actually saying you should be off. So rung 1 quickly said you should be on, but instantly when it got to rung 2, solving rung 2 logic, it said you should be off. So they kind of oppose each other. And therefore that's where the destructive bit terminology kind of comes in, because they kind of cancel each other out or destroy each other in this case. So again, it allows you to do this. So this is one of those things to always have to be mindful of, is that it does allow you to do this. But as you can see, it can kind of create some significant havoc in the program. Now let me go ahead and I'm going to turn off my start switch, and I'm going to toggle this tag off. So I broke the latch basically, and everything's turned off. Now let me turn on the load switch. So the load switch is input 1. Now when I turn on the load switch, look what happens. The B conveyor turned on, but also the B conveyor turned on up here in rung 1. It shows it as being energized. Even though nothing here is true, that should be allowing it to turn on right now. But again, because of the way we solve our logic, rung 1, then to rung 2, well, rung 2 says you're on. So when it comes back to the top of the sweep again, it says, oh, rung, conveyor B, you're on. So so it's showing that it's energized. So really, it got down to the fact that duplicate coils are just bad programming practice. Again, not illegal and allowed in the program, but can definitely create situations that we don't want to see happen. So, what is the solution to this problem? It's actually quite straightforward. What we would have to do is, instead of trying to do these two rungs in this manner, we would actually have to have a separate rung that would control just conveyor A only, and then a separate rung that would just control conveyor B only. And basically this logic that would be controlling conveyor B up here in rung 1, and this logic that's controlling conveyor B in rung 2 basically would be copied into this new rung, and we'd be kind of in parallel, right? So we have two paths that could turn on conveyor B. Path 1 would be kind of this situation. Path 2 would be this situation. So being that that is considered an OR, right? Path 1 or path 2 would allow conveyor B to be turned on. That would be a parallel, basically a parallel branch. So we would have a parallel branch that would have conditional logic for this first condition with the start switch, and then we'd have the second parallel, the parallel path that would have the logic, when the load switch was told to be turned on. And then we'd probably have a third rung, of course, that would also control the load conveyor. You could potentially do the load conveyor. Well, I would do it separate. I was going to say you could potentially do it in parallel, but no, that would not really work. So we want to have the load conveyor in its own third separate rung as well. So basically, long story short, although this looks nice and was very concise approach and just two rungs and pretty straightforward, sometimes we want to see our logic kind of broken out into separate rungs. Even though it takes more programming, it just sometimes it's a cleaner way to go. So rung 1 would be all the controls for conveyor A. Rung 2 would be all the controls for conveyor B. Rung 3 would be all the controls for the load conveyor. And then, of course, being that we also have to do the load conveyor again and the left or right conveyor, depending on which direction we move the box in, we would probably have a fourth rung that would be controlling those left and right conveyors as well. Okay, so hopefully this helps explain a little bit more. So next time in the lab, we'll come back into this, and then we'll kind of go back to the drawing board, so to speak, and see if you can redesign the program and get around this situation with the duplicate coils.